Okay, great. Good morning, everyone. So today I'll be giving my talk on fermion-qubit mappings and the ZX calculus. So without further ado, let's get into explaining what these things are and how they're related and why anyone would want to study such things. Slight word of warning is, anyway. I'm going to start by going over a bit of the background of what is a fermion-qubit mapping, what is the ZX calculus, and then I'll talk a bit about each of the different sections of the paper. So we'll talk about linear encodings, what they are, and how they're related to the next part, which are ternary tree mappings, and then maybe we'll have time to talk about some local encodings in the end. I sort of originally made this slideshow for a much longer talk that I gave before, so don't be too alarmed if I skip some slides just to keep us within the 20-minute time limit. Let's talk about some of the background. So, why fermion-qubit mappings? Why fermions? So fermions are it's a large class of subatomic particles that make up the things that make up atoms, like protons, neutrons, electrons, all the things that we'd want to understand if we're looking at, well, atoms. And historically, these atomic systems have been quite expensive to simulate on classical computers, and we hope to use the quantumness of quantum computers to help us in simulating these systems and understanding problems in chemistry and condensed matter physics a bit better. That's the ultimate goal of this, is to simulate these systems on a quantum computer. So mathematically, a fermionic system is described by the fermionic operators, those being the creation and annihilation operators. Sometimes these you can see these things being referred to as raising and lowering operators. You can imagine that a creation operator creates a fermion where there isn't one, and an annihilation operator takes a place where there is a fermion and makes there not a fermion. That's sort of a very hand-wavy way of saying it, I think, but I'll explain what I mean. So the fermionic state space is spanned by these things, which I call curly kets, because this bracket is curly. Is to distinguish it from qubit states. So it's a basis of bit strings, much like the computational basis of qubits, where if we have a 1 in the ith spot, it means, so if ni equals 1, what that means is that there is a fermion in the ith spot. And so what the operator ai does is that if there is a 1 in the ith spot of this vector, it will turn into a 0 after an application of ai, an annihilation. And there'll also be some phase factor involved, some -1 to some power. The reason we need that is because these fermionic operators are required to anti-commute with each other. So we're sort of, by adding a minus sign, which I'll show you in a moment, we're sort of keeping these things in anti-commutation with each other. Equivalently, a fermionic operator can be described, a fermionic system can be described by the Majorana operators. So instead of having n creation operators and n annihilation operators, we can sort of have 2n of these Majorana operators, which it's quite easy to translate from Majorana to creation annihilation, and they have their own little anti-commutation relation as well. Okay. Say about fermionic operators? I don't think so. I'm ready to define the main object of study of our paper, which is a fermion-qubit mapping. So a fermion-qubit mapping is an isometry that goes from the fermionic space of curly kets to the qubit space of what you might call quantum kets or quantum states. You all know what the qubit space looks like. But yeah, the simplest example of a fermion-qubit mapping is the Jordan-Wigner mapping, or the Jordan-Wigner encoding. We use the terms mapping and encoding sort of interchangeably in this subject. So what the Jordan-Wigner mapping does is it takes a bit string, a basis vector associated with a bit string in the fermionic Fock space to the qubit state represented by the same bit string. And if you look at what that does to the fermionic, if you either look at creation annihilation operators or Majorana operators, you'll see these trailing Pauli Z strings. So these are these X, Y, and Z are the Pauli matrices. So it's these chains of Zs that keep the anti-commutation relations going, because they're sort of they're carrying the phase factors, if you know what I mean. Because Z it's a phase flip. Yes, it is. Okay, how are we doing for time? Okay. So from now on, I'm going to abuse notation a little bit and say, well, we're studying fermion-qubit mappings, the mapping that goes all the way from the left of this expression to the right of this expression. But we're sort of going to factor through Jordan-Wigner, and we're going to just study the qubit isometry part of it and not think too hard about Jordan-Wigner happening under the hood. We're just going to sort of take Jordan-Wigner for granted now that we've introduced it, and we're going to deal with the part of it that's a qubit isometry. But don't worry too much. It's not that big of a change. Okay, now the ZX calculus. Some of you may have seen this before. If you have, great. If you haven't, don't worry too much. The main takeaway is that it's a graphical language for representing linear maps on qubits. It's found uses in all sorts of areas of quantum computing. I couldn't name all of them off the top of my head, but it's been used in quantum error correction, quantum chemistry, circuit synthesis, really all sorts of things. But I shall digress a little bit. It is generated by, so these things here are called spiders. You can sort of see why if you look at them. They've got a lot of legs and a circle in the middle, kind of like a spider. You can think of them as being a bit like this green one being a rotation around the z-axis on the block sphere, or the red one around the x-axis. These are sort of the Z gates and X gates, or Z spiders, X spiders. Hand waving a little bit to save time, but yeah, the thing is, you can rewrite diagrams from one form to another form while still representing the same linear map, just by using these rewrite rules in the box. So you can fuse spiders together. You can change the color. This yellow here represents a Hadamard gate. Yeah, this is a Hadamard gate. Yeah, one wire is one qubit. If you've never seen this before, don't worry too much, because we're going to use something that I think even fewer of you would have seen before. I hadn't seen it before I started working on this paper. The scalable ZX calculus, which allows us to deal with whole registers of qubits at the same time. So it's just a bit more machinery that will allow us to sort of divide and gather registers of qubits, apply these Z and X transformations to multiple qubits at once, and most importantly for us, implement these matrix arrows. So if A, this A here is a matrix over the field with two elements. So you remember how the basis vectors of the qubit space are given by n bit strings of length n. So a bit string of length n can be thought of as a vector in the field of two elements to the n. So this x in f2 to the n means it's an n long bit string of zeros and ones. So under the interpretation of x as a vector in f2 to the n, this matrix vector product here, a times x, is well defined. And if we consider the map that sends each x to a times x, that extends to a linear map on the whole qubit space. And we will want to implement these sort of maps for reasons that will become clear in the next section. Okay, don't worry too much about these rules. These are just more rules about how matrix arrows interact with the rest of the scalable ZX generators. I won't go through any of the nitty-gritty in this presentation. The paper is out on the archive though. It has the same name as the title of this talk. Yeah, something I should say. Okay, that's enough on the background. Let's talk a bit about linear encodings and ternary tree mappings. I'm hoping I can get to the end of ternary tree mappings, and I'll be satisfied. So what is a linear encoding? So a linear encoding, or a linear fermion-qubit encoding, is one where we start with a fermionic state, and we map it to the qubit state through a binary matrix, an invertible binary matrix. Yes, it has to be invertible and n by n for now. So we have to have as many qubits as we have places where a fermion could be, or fermionic sites. So yes, this diagram here means that we can represent this as sort of having a bunch of Z spiders on one side and X spiders on the other side, and sort of the ith Z spider is connected to the jth X spider if aij equals 1. It's convenient for working with. Give me one moment. So what we want to do is to figure out what an operator looks like under this this is a mapping of vectors or a mapping of states on the state space. But it would be nice if we could see what the fermionic operators looked like after undergoing this transformation. So we're going to do a bit of sort of change of basis, if you want. So imagine, okay, I'm going to take for granted that if you put a matrix arrow that's invertible and another matrix arrow with the same matrix going the other way, they cancel out. That's a fact that if you're good with matrix arrows, you might be able to see how to prove it, but don't worry too much. This is sort of what this operator here is. It's sort of like when you do change of basis. You have the change of basis matrix on one side and its inverse on the other side. So if you just look at the left and right hand sides of this equation, you can sort of imagine taking this OJW, this Jordan-Wigner operator. If you can somehow get it through E and get it to come out the other side without damaging E, you'll get the operator you want. And that's why we call this technique pushing through the encoder. Okay, I'm going to show a couple examples of linear encodings. So we saw the Jordan-Wigner encoding already. That's just if we take A to be the identity matrix. There's also the parity encoding, which is interesting. It eliminates the trail of Zs that Jordan Wigner was giving us. Yes,
Hey,
can
yes.
you still hear
Just
me?
a quick question. How long will you
Sorry.
continue your talk?
Probably 5 more minutes. I
Is
think
that
I
okay?
can get to the end of.
Okay, yeah.
Yeah, I can wrap this up in 5 odd minutes.
Okay, great. Thank you.
Yeah, I'll just I'm gonna get to the end of linear encodings quite quickly and then just talk about ternary trees, and that's fine. So yeah, I won't talk about parity then. I think the Bravi-Kitaev encoding is a lot more interesting because what it does is it sort of as you go up in each layer. So it's defined recursively on matrices as follows, where this A is this. It's a matrix that's all zeros except ones on the bottom. The takeaway of the Bravi-Kitaev mapping, though, is that you can prove that the fermionic operators it produces have log weight. So the number of qubits on which these operators act is logarithmic in n, which is the size of the circuit here. So it's a cool fact, which I believe is in the paper, but unfortunately I don't have time to go over it because I have to move on to. I'm going to gloss over that and talk about ternary tree mappings. So yeah, what is a ternary tree, and how is it related to linear encodings or any of this stuff about fermion-to-qubit mappings? So a ternary tree is simply any tree where each node has at most 3 children. How does one make a mapping out of a ternary tree? Well, you sort of look at the paths that go from the root of the tree down to its leaves, and you label the top, middle, and bottom branches by X, Y, and Z respectively. And if you trace all these paths out, so X, 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 Y, X, it gives you Pauli strings. And a collection of Pauli strings, the particular collection of Pauli strings that come from any particular ternary tree can be put together somehow in details which I will gloss over now, but are available in the paper, to turn this into a fermion-qubit mapping. You basically make the Majorana operators these things. Okay, the main result of the paper that me, Razin, and Leah have written is that we can translate ternary trees to ZX diagrams. In other words, every encoder that comes out of a ternary tree is a linear encoding with a ZX diagram. We can extract the matrix arrow from it, like so. So at I'll do an example. Here we go. Here's one I made earlier. So if you look at this ternary tree example, and you at each step replace the nodes of the tree with this sort of piece of scalable ZX technology, it will reach, and then you apply simplification rules, so you do some things, you'll eventually reach a diagram that looks like this with Z's on the left and X's on the right. And from this you can extract, did I put the algorithm? Yes, I did. You have an algorithm for going from a ternary tree to a matrix, and it's a recursive algorithm. So you go sort of from the top of the tree, you go down one, and then you do the same thing again. I wish I had time to show you a bit about this proof. It's a very nice induction proof. It's the main theorem of the paper about how essentially, if you start at the top of the tree, you consider the subtrees about down the X, Y, and Z branches, and down each of these subtrees, you can sort of you can massage this diagram to get it to look like it's in matrix arrow form already, and then read off the matrix. and then you would apply this this result inside the subtrees as well. And this is the pseudocode for the algorithm. I don't think I have time to talk about local encodings. Are there any questions? Because I realize I did go quite quickly. I should ask the floor if there's anything that's...
Yes. Maybe we have time for one question.
Okay.
So first of all, thank you. Then number one. And then the second question is like, is there a question from the audience right now?
I actually didn't hear. Did someone ask a question?
No. There was an applause.
Okay,
yeah.
I didn't hear it, but thank you.
I have a question. Thank you for your talk, and it's more a curiosity. But because in this talk you have used ZX calculus to encoding to model the encoding from fermion to qubit, and my question is, can you use like all the rewriting techniques and optimization techniques for ZX calculus in this scenario? I mean, first of all, this technique makes sense,
Yes.
and if yes, can you?
So the rewriting techniques, that's sort of what we do to simplify our diagrams from say something a bit ugly. When you say the ternary tree to ZX translation that we have, it starts looking a bit like this, and then we sort of use the rules of the calculus to massage these diagrams into looking a bit nicer. I guess that's sort of taking advantage of ZX normal forms. Optimization techniques. Let me think. Are there any in here in particular? I use quite one thing I glossed over is the representing Hamiltonians in full using the ZX calculus. But yes, in this process of simplifying these diagrams down, we used quite a lot of different rules, sort of more general versions of rules to simplify these. Yes. So yeah.
All right.
Thank you.
Okay, thank you very much. Thank you very much.
Thank you, guys.
Yeah, you can't hear
Sure.
the audience here, just we have one mic that I can talk to you. Let's thank the speaker one more time.
Guys.